Well, here we've got a review of strong acids. It's going to be a short review, and as long as you've already covered this topic ahead of time, I think it'll help you. But if you haven't really covered this stuff, this is going to go too fast. Well, here we go. Strong acids. They're the first part of acid-base equilibrium, but it's not much of an equilibrium. First of all, there's not many strong acids. We've got 6 here. We've got hydrochloric, HCl, nitric, HNO3, our sulfuric. These are really the common acids that you'll find in most labs. The thing about these strong acids is when you dump them into water, they completely change the water. They dump their proton successfully onto the water to change it to H3O+. This is the stuff we measure the pH of. This is what we're concerned about in aqueous solutions. And then this A-, this other half of them, the chloride, the nitrate, the sulfate, the bromide, iodide, and the chlorate, they're pretty much spectator ions in terms of acid-base reactions. These A- can be pretty well ignored, and we just say, okay, the strong acid makes H3O+. Now, to keep things simple, very often we'll just say H+, the simple proton. That makes things a bit easier. The conjugate base, the A- is stable, and they're stable because of resonance and the size of their atoms. And the more stable the base is, the less likely it is to pick up the proton and turn back into the conjugate acid. These ultimately float around as spectator ions, and no reverse reaction occurs. This reverse reaction is not going to happen. Big X. No way. The reverse reaction doesn't happen at all. We're going to be stuck. Any HA becomes H+ and A-, because all strong acids ionize into H+. You can find the pH of the solution very quickly and easily by taking the negative log of this stuff. Even though it's all changed to H3O+, you know its concentration, because they'll say, oh, we made this acid up as 1 molar. Really, you're making up the H3O+ as 1 molar. You simply take the negative log of the H3O+ or H+, which is the concentration of the strong acid, and you've got the pH. And we know about pH already in terms of the lower numbers. As a consequence, because these things 100% ionize, you'll find that it doesn't take much to get a very low pH. Like only 3.6 grams of HCl in a full liter of water, like 4 quarts, produces a pH of 1. So you get this pH of 1 almost immediately. In fact, if you have just 0.03 of a gram of HCl in 1 liter of water, you have a pH of 3. So in fact, it's very difficult to get a pH of 3 with hydrochloric acid. I mean, all you've got to do is wave this bottle around this water, and you've got a pH of 3, and a couple of more drops of HCl, and it whips to 1. So virtually any solution of hydrochloric acid or any one of these strong acids is going to be 1, 2, but keeping something with a pH of 3 with a strong acid is like impossible, because, as I say, just 1 drop more and it turns into a pH of 2, another drop, and you get pH of 1. Strong acids typically, even their dilute solutions, will have low pHs. When strong acids have an acid concentration greater than 1/10, their pHs have become less than 1. And rather than using pH, we just switch to molarity. I mean, who wants to deal with the negative pH numbers at all? In fact, even a pH of 0 is problematic. We're going to find out that when we react strong acids, that it's an all or nothing thing. So when you start off with a titration, when you add base to any strong acid, you're going to start off at 1. And it's going to stay at 1 and stay at 1 until the acid's pretty well taken care of. And then just within a couple of mLs, the pH will flip over. It's going to be a flat curve here and then zap to an equivalence point once you've neutralized. Because look here, we've got a pH of about 1, pH of about maybe 1.4, pH of about 1.9, and then within 1 ml, zap, we move up to the equivalence point, 7. And in fact, it's very difficult to get this exactly 7, because an extra drop of sodium hydroxide is going to whip it over up here to a pH of 12. So pHs, titrations of strong acids are pretty boring at first. They just 1, 1, 1, 1, 1, 1. Then all of a sudden, bang, you get up to 7. This is a classic for it. Well, that's pretty much it for strong acids. And we'll switch over now to strong bases.
Okay, now for some strong bases. Here we go. The strong base is hydroxide, which is, there are some things that are strong bases besides hydroxide, but they're not an AP. They're pretty exotic compounds like hydrides that all will react to water to make hydroxide. So only strong base you've got to worry about is the hydroxide base, and it's typically attached to a soluble ion like sodium or potassium. So now here I've got a picture of some sodium hydroxide. It's in pellets, it comes in flakes. This stuff, along with potassium hydroxide, absorbs humidity from the air. If you leave this out in a humid room within an hour, they'll all glisten, be covered with water, and eventually turn into a puddle of concentrated sodium hydroxide solution. And as soon as they start getting wet, it's concentrated sodium hydroxide, and you can get hurt badly with that. And we're dealing with a pH of 14. So you dump this stuff into some water very, very carefully. And don't dump much in because it's a very exothermic reaction. The water will start boiling and splattering. And if you're nearby, you're going to be the Phantom of the Opera because this stuff dissolves flesh beautifully. Nasty stuff. Very, very careful with sodium hydroxide. I recommend gloves and having some vinegar by when you've got these solid pellets. It doesn't take much and water to change that pH to 14, but if it's dilute, you'll still have a pH of 14. Another thing is this absorbs carbon dioxide from air, with air. If you've got some CO2 in the air, which you have, it'll change the sodium carbonate and neutralize itself. That's our strong hydroxide, but how do we deal with it in terms of AP and pH and stuff like that? Ionic compounds with hydroxides dissolve to produce hydroxide ions. Water normally, when it's neutral, has a balance of equal amounts of H plus and OH minus, and both of them are present in very, very small amounts. At room temperature, because a neutral solution has these two concentrations equal, each one of these will be 1/10 millionth molar, 10 to the negative 7, our pH of 7. When it's hotter, both these concentrations will go up because this Kw will increase with temperature too. In fact, be careful on AP exams because the definition of neutrality is not 10 to the negative 7 molar H plus. It's H plus times OH plus equals whatever the Kw of water is at that temperature. Room temperature is 1 times 10 to the negative 14, so we've got that 7. So therefore, at room temp, 25 degrees Celsius, the H plus will be equal to the OH minus, both 1/10 millionth molar. So, okay, now if you end up adding sodium hydroxide to water, which has got this beautiful balance, where there's not too much hydroxide, there's not too much H plus, and we consider it to be perfectly neutral, you soup up the hydroxide ion concentration. This goes up, and the H plus goes down. The balance is messed up. This is where we sort of get into a convenience factor. Solutions, in terms of acids and bases, are described just with the H plus and with pH. So when you're talking about a basic solution, you tell people what's happening to the H plus, even though it's the OH minus that's creating the problem or creating the alkalinity. If you want to find out what a strongly basic solution is, you're going to have to deal with figuring out what's the pH as a result of it. There are two ways to solve for this. You can solve for the H plus using that Kw equation that we had on page 1. You plug in the concentration of the hydroxide and then calculate the H plus. And with the H plus, then you do the negative log of the H plus and you get the pH. Another method that you should be fluent in is to take the negative log of the hydroxide ion concentration. That gives you the POH. As soon as you find the POH, they both add up to 14. If you're good with logs, you know why this would happen. These log things are really neat. There's the two ways. You can use the Kw or you can use this pKw. This little chart's a good one. This is one of my favorites. Hubert Allier was one of the great chemistry teachers. I was lucky enough to have him as a teacher. In fact, when he taught at Princeton, he would have Einstein come in to listen to his classes. That's how good his chemistry class was. He came up with this chart. Here we are at 7, where they're balanced. 10 to the negative 7, 10 to the negative 7, pH of 7. As we add extra hydroxide, it squeezes down the hydrogen ion concentration to 10 to the negative 14. Take the negative log of that, and you get a pH of 14. And here we've got the pOH at the bottom. This chart should make sense to you. You should see it in terms of this logarithmic ratio and concentration in terms of molarity and pH and hydroxide and pOH. Now, titration is going to be, it's the mirror image. This is like the mirror image of the strong acid. Usually, getting a pH of 14 is like getting a pH of 0. It's really, really tough to do. But 13 is pretty much where you start with. And, you add acid, and still you're at 12, 13 until zap. Within 1 ml, you go from a pH of 12 to 7 at the equivalence point. Now, one thing I didn't include in the last slide on acid and bases is this equation. At the equivalence points, the concentration of the acid times the volume of the acid equals the concentration of the base times the volume of the base. This is a handy one. You're going to use this somewhere on the AP exam. In fact, let me put that very, very useful 1-to-1 ratio when you're doing monoprotic stuff. And it's a fast, easy way of things. I mean, here's the concentration of the acid. Here's the volume of the acid. Here's the concentration of the base. Okay, easy solution. Okay, that's our strong base. And now for the really challenging thing next, which is the weak bases and acids.